In this video, we're going to talk about the effect of Le Chatelier's principle on dynamic equilibrium examples in terms of pressure, temperature, catalysts, etc. So let's start by talking about equilibrium in itself. Now, this is the same as GCSE, and you can see the graph here. And the graph here is of the Haber process. So the Haber process, nitrogen plus hydrogen going to ammonia. You notice they're all gases, okay, and that's what you'll do in the first year of your A-levels, just this called homogeneous equilibria. Now, if we look at this example, we can see over here I've got the orange is the hydrogen and the yellow is the nitrogen. So that means at the start, the orange and the yellow, they're the reactants, they are reacting and then going down like this. Okay, and then it makes sense right at the start of the reaction, the product, which is the red one, you can see over here the product, which is NH3, is going up. And then they get to a certain point where the concentrations do not change. Okay, and that is the point where you have got to equilibrium. So if you're in a question that's in an exam and you're asked to say things about equilibrium, say, how do you know it's equilibrium? It's because the concentration does not change. And that means of all of the reactants and the product, concentrations don't change. Now, if we move on from here, and we just say, right, okay, what's our actual definition of equilibrium? This is what we see if we monitor the concentrations in equilibrium, but actually what's the definition? The definition is the forward and backward reactions are at the same rate and they're in a closed system. Closed system just means it has a lid on, okay? So it's just sealed, a sealed system, okay? And that forward and backward reaction rate is the same, and if the rate going forward is equal to the rate going backwards in this reversible reaction, the concentrations won't change. And so it's all linked together. Now, I told you there's two types. So two types is, first of all, the homogeneous equilibrium when the reactants and products are in the same state. So you can see these are all gases, but it can be when any state, just where the reactants and products are in the same state. And that's called homogeneous, as in the same equilibrium. Now, the one you're going to do in the second year of your A-levels, but I won't go over in this video other than this, is when you have different states. You can see liquid, gas, and solid there. That's called heterogeneous equilibria, and that's just where the reactants and the products are in a different state. Now that we know that the equilibrium is when the concentration doesn't change and the forward and backward reaction rates are the same, we can see how Le Chatelier's principle affects that position of equilibrium, whether it goes to the right or it goes to the left. So it goes towards the products, which is to the right, or makes more reactants, which goes to the left. The position of equilibrium of a system changes to minimise the effect of any imposed change in the conditions. Now, you don't really have to remember the definition of Le Chatelier's, and it sounds a bit confusing, but it's actually really quite simple. So if you impose a higher concentration, the system will do the opposite. So it says minimise the effect of any imposed change. Well, the imposed change is the higher concentration, so I want to minimise the effect of that by lowering the concentration whatever has been increased. So if I add acid, high concentration of acid, the system is going to want to lower that concentration of acid, and it's how it does it, which is the key to answering the questions. So the same thing is if you apply a higher pressure, well, the system is going to want to lower that pressure. It's going to lower that pressure, and it's how it does it and why it does it, which we'll go on about later. And again, the opposite of this, if you lower the concentration, it's going to want to increase. If you lower the pressure, it's going to want to increase as well. Now, if we go for a higher temperature, the system will lower the temperature. That doesn't mean it'll bring it back to its original levels, just lower it from where you've brought it to. And again, with all of these, it won't bring it back to its original levels, it will just lower it from where it was in the first place. And the equilibrium will either go to the right or the left to make this happen. And we'll talk about examples of this now. So the first one is the effect of concentration on equilibrium. And the best way to think about it is just in a simple 1-to-1 ratio. Now, if you want to go over further examples of this, there is an exam-style questions video after this, which goes through specific examples of reactions. We're going to just use in this video A and B. So if we go from A to B, let's imagine we have 4 moles here. So imagine this is 4 moles per decimeter cubed. And imagine B is 2 moles, because we've got 2 blue balls here. Now, Let's look at the concentration and the position of equilibrium. Now, everything I highlight is going to get you a mark in the exam here. So they're the bits you really need. I'm going to put more writing in here just to explain it, but actually the orange parts are the marks you're going to get in the exam. So there's a higher concentration on the left of the A, okay, which means you'll get a higher frequency of collisions, okay, of A particles colliding together. That means you'll have a higher rate going forward. Now remember, the rate goes forward and it goes backwards, which means if we look at the particles of B, okay, there's less particles of B, which means there'll be a lower frequency of collisions, which means they'll react less to turn back into A. Now here I put 2 boxes, but remember these are all mixed up in one pot. I just put the 2 boxes just to make it clear of what's changing. So if we look here and we do what we say, well, the equilibrium says I've got a higher concentration of this, which means that has a higher concentration. So I'm going to lower that concentration. And the only way I can lower that concentration is by making more of the product B. Okay, so let's just go back here like this. You had a higher concentration here. Okay, that means there's a higher frequency of collisions. The only way I can lower the concentration, because I've got a higher concentration here of A, is to react it to make B. And so I'm going to make B. Now that higher rate of the forward reaction, okay, happens until you get to some form of equilibrium where the concentrations don't change. And in this simple example, you can see it makes sense. There's 3 moles per decimetre cubed of each. So the equilibrium has moved to the right, okay, as the reactants have a higher concentration, and it means you have a higher yield. Yield is always referred to as the one on the right, okay, as the product. Now, this happens until the equilibrium is reached and will be different for each reactant. Now, I've shown you a really simple example here, but you can get much more complicated examples, but the principle is the same. If you increase the concentration of one thing in the reaction, Le Chatelier's principle says that the reaction itself will lower the concentration of that, and it's usually by going in the opposite direction to make the product. Okay, and it's usually if you add more reactant, you're going to make more product, and it makes sense because of frequency of collisions. So now look at the effect of pressure on equilibrium. And again, we split it up in 2 boxes, but remember this is all in one box. And the reason why, or one container, the reason why we put it in 2 boxes is just to make it absolutely clear. So let's imagine we've got 2A to B. That means the ratio of A to B is 2 to 1. So we've given you a ratio here in the stoichiometric ratio in the equation. That just means the balancing in the equation, 2 to 1. So you see 4 to 2 is 2 to 1. So let's have a bit of imagination here and just say that we know this is the higher pressure and we know that is the lower pressure, because there's higher pressure depends on how many particles you have in a set size container. There's more particles here, okay, more particles colliding with the edges of the container, okay, and therefore you've got a higher pressure. Now, if we look at this, what happens if we increase the pressure? Now, how do we increase the pressure? Either put more particles in, or what we can do is lower the size of the container. So if we lower the size of the container, it's currently 1 decimetre, okay, and that would mean that this is 4 moles per decimetre. Let's count each one of these balls as 1 mole, okay, so that's 4 moles per decimetre cubed, and that is 2 moles per decimetre cubed. And now what we're going to do is change the size of the container to show that we're increasing the pressure. So here you have that. So we've taken that from 1 decimetre to 0.5 decimetres, and then what would happen to the concentration if that was the case? So we've now got 4 moles, but we've got it in half a decimetre. So that means in 1 full decimetre, we would have 8 moles. And then in 1 full decimetre, we would have 4 moles. Okay, so that means that if you look at it, this has gone up by 4, and this has gone up by 2. So if I increase the pressure, the actual concentration of the A, the higher pressure side, has gone up by more than the lower pressure side, B. Okay, and that's the way it works in terms of you increase the pressure. It's a really easy way to understand it. So the side of the moles, side that has the most moles has the most pressure, and it will increase more when you increase the pressure. So that concentration will increase more when you increase the pressure. Now, how do we actually answer the question? So if we increase the pressure, side with most moles would increase its concentration more. We know that. And that means there's a higher frequency of collisions, which means the forward reaction rate will go up. But the answer in the exam is the equilibrium will move to the right because the forward reaction rate will go up, okay, and therefore you will get the side, it will go to the side with the least moles. So if that, I'll say that again. So basically, the 4 moles has gone up to 8 moles. It's higher than the side with the least moles. That will react more. Because it reacts more, equilibrium will go to the right. Okay, and because it goes to the right, it will go to the side with the least moles because essentially this has the most moles, which is why it's reacting more. And so the green part there is what you say in the exam. Equilibrium will move to the right, and that's because it's the side with the least moles. And that means you'll get a high yield of the product, which in this case is B. So let's now look at temperature. So temperature doesn't matter about the stoichiometry of the equation, what numbers you've got here. So it doesn't matter. Okay, what you're looking at is the value of the enthalpy change of the reaction. Is it endothermic or exothermic? So hopefully as you look at that, you see it's a positive number. So this is going to be endothermic. Okay, and that means as you do this reaction, it takes in energy from the surroundings, which means it's going to get colder, which is why we've put it in blue. Okay, now, so it's going to get colder the more of B you make. Okay, and it will get hotter the more of A you make because it's exothermic in the opposite direction. So what happens if we increase the temperature then? Well, first of all, let's just go back to what it said and say which is the hot side and which is the cold side. So the higher temperature would be if you make A, and the lower temperature would be if you make B. Now let's have a look at what actually happens to the temperature and the position of equilibrium. So remember, it's going to do the opposite of what you apply. So what happens if we increase the temperature? It's going to want to decrease the temperature, will decrease the temperature. It will decrease the temperature by doing whatever way it can do to decrease the temperature. And the only way to decrease the temperature is to make more of B, because if we make B, we lower the temperature. So if we increase the temperature, it would increase the rate of reaction of the endothermic reaction, which is the forward reaction. You can see from this number here. Okay, and that's what you have to say in the exam. It would increase the rate of reaction of the endothermic reaction. You can also say forward reaction if you want, if it is the forward reaction. And remember, this is totally dependent on what the reaction is. This is an endothermic. It will be a different answer if it's exothermic, because obviously exothermic makes it hotter, endothermic makes it colder. Anyway, so in this example, we have increased the temperature. The system is going to lower the temperature. It lowers the temperature by following the endothermic reaction. Equilibrium therefore moves to the right, okay, and you get a high yield of the product, which is B. So we're now going to look at the effect of catalysts on the position of equilibrium and how quickly that equilibrium is established. So let's look at an example first of all, which is hydrogen peroxide. Hydrogen peroxide uses many catalysts, manganese 4 dioxide, liver, potato, everything if you do in your bio classes, and it's an exothermic reaction. So if we put that down here and we put it on an enthalpy diagram, we can quickly show you how a catalyst works, or remind you how a catalyst works. And you can see that the activation energy, definition down there, minimum amount of energy required for a reaction to occur, is going to appear here. Now that is normally your breaking of bonds, your activation energy. Let's just say it's 75. Now, when you add a catalyst, you get a different intermediate, and that intermediate, for example, will have a lower energy, and therefore the activation energy with the catalyst will be lower. Now, this is not to scale. I know it says 75 to 8. I had to make it much larger just to make sure you could properly see. But you can see that it's gone down, okay, and you can see that's done with a catalyst. Now, if we do this with another example, and this time we do it with a hard process uses iron as a catalyst. Okay, so let's do this again. Okay, but we're going to put iron on. So can you draw, stop the video, and draw out what this would look like with a catalyst? Okay, you don't need to have it to scale. So what you would do is you put your exothermic diagram on, because you've got minus 63 up there, minus 63 down here. The arrow is pointing downwards. Okay, there's no double-headed arrows, just an arrow pointing downwards because the energy is going down. Then you've got your arrow that's going to go up to your intermediate. Okay, this is your normal reaction profile, but now you're going to do it with a catalyst. You're just going to lower the energy of that intermediate and lower your activation energy, and that's your activation energy with an iron catalyst. Okay, now really important thing, this is the exam part, in the reversible reactions, catalysts speed up both the forward and backward reactions. So it absolutely does not change the position of equilibrium at all, because it's speeding up the forward and it's speeding up the backwards. Now, can you think of any other effect that might make? What that does is the equilibrium position doesn't change, because again, speeding up the forward reaction and increasing the rate of the backward reaction, but it does it in a faster time, so it takes less time. So actually, in terms of why would you do it in industry, why would you add a catalyst? Well, you're going to use less energy to make this thing happen, and it's going to take less time to make it happen at the same time, and that means less energy as well, less costs in terms of electricity or fossil fuels or whatever you use to heat your reaction. So a catalyst conserves your energy, okay, and means less energy is used, and therefore, in the end, less costs. So we'll show you this in a pictorial form here. So here is the graph from earlier, which is the Haber process. And we know it took that amount of time to get to equilibrium without the catalyst, where the concentrations are not changing. So could you redraw this, but with a catalyst? Okay, so if you want to, stop the video and try and do it now, okay, to try and test yourself. But we're going to do it here. Can you see that what we've done here is just the line has become more steep, and then it's got to this equilibrium at a less time. And this has got to equilibrium at less time. So our equilibrium is in fact here. And that's with a catalyst and achieved in less time. And that is why you use a catalyst. Okay? Remember, the equilibrium position does not change, but the equilibrium is reached at a faster rate in less time. We're now going to talk about the compromise between yield, which is decided by chemical equilibrium, and the reaction rate. They are completely separate in terms of how you think of it in terms of industry. So let's think about this in terms of industry. We've got the Haber process. Now this question can be about different reactions and has been in the past, but most of the time it's about the Haber process. So the two conditions you need for the Haber process are high pressure and low temperature. Now, why is it high pressure? It's a high pressure because if you apply a high pressure, Le Chatelier says it will do the opposite. It will lower the pressure. It will lower it from that higher pressure by going to the side with the least moles. The side with the least moles is the products. So you will get a high yield. So high pressure will give a high yield because you're giving more product. If you apply a low temperature, the opposite of a low temperature is a high temperature. So the reaction will seek to increase that temperature that you've applied. You applied a low, it's going to seek to increase it. It can only increase it by following the exothermic reaction, which is minus 63, which again will make more products because it's exothermic in the forward direction. Now, the question is, and the question will be, what are the actual conditions? Okay, they may ask you to determine the conditions in terms of yield and the conditions in terms of rate. So the conditions in terms of yield are high pressure and low temperature, and that will get you a very high yield. Okay, but if the pressure is too high, it's too expensive to safely contain the reaction. So very simply, you can't run it at that pressure because it's just too expensive for the company to do. Remember, higher pressure also means higher rate. Okay, so they would like to have it at a higher pressure because they get a higher rate. The reaction happens quicker and they get to equilibrium quicker, but they can't because it's too expensive. Next thing, the lower temperature gives a lower rate of reaction and so takes a long time. So you'll get a high yield, but you'll get it over a longer time. Okay, so I always give this simple example to my students. Let's imagine you do the reaction and in 10 hours you get 9 tons. And 9 tons, if you calculate it, is a 90% yield. Well, that's really good. You got a really high yield. Did it in 10 hours. It took quite a long time to do it. What if you change the reaction conditions and this time you apply a slightly higher temperature? You might get in 1 hour, you might get 4 tons. It's a 40% yield at a higher temperature. So this is a high temperature and this is your low temperature. The higher temperature, you get 40% yield, but you could repeat that reaction every hour. If you repeat it every hour, that means in 10 hours, it gives 40 tons, which is a much better, a higher amount of your ammonia than just doing it at that low temperature. So what we have is these two conditions. 200 atmosphere, that's 200 times the pressure in the room that you're in right now. It's not so high to be expensive, it's still not low pressure because it's 200 times room pressure. Okay, and also 450 degrees Celsius. 450 degrees Celsius is a higher temperature than you would want, but it's increasing the rate. So it means that you will get as much ammonia in as little time as possible. And that's the key thing you need to say at the end as your evaluation. Okay, so first of all, you need to determine what are the actual yield conditions. Well, high pressure because it goes to the side of the least moles, low temperature because it follows the exothermic reaction. Okay, but we don't do that because the pressure is too high, it's too expensive. We don't do that because a low temperature will give a lower rate. Okay, and knowing the actual conditions is required, and you really do need to just do a final evaluation like that at the bottom. So as you can see from my change in clothing, we thought we'd add a little bit more extra to this video just to give you an example of where you might see this in an actual practical example. So you can see here that I have got chromium. The orange one is chromium Cr2O72-. And what I'm doing is I'm adding, and I'll show you here because it's going to come across here. Hopefully this will carry on. Okay, it can be converted into and back again. So I started with the orange, okay, and I went to the yellow. Okay, but you can do that by adding acid or adding alkali. Okay, so if you add acid, the equilibrium shifts to the right. Okay, so if I add acid here, the equilibrium will shift to the right, okay, and it will go orange. If I add alkali, it will remove the hydrogen ions, which means the system will want to go to the left and replace the hydrogen ions, and it will go back to yellow. So let's go back again and look at this video. Okay, and see if we can get it going again. There we go. So you see here, I must have added what to here to make it go yellow? Must have added alkali to make it go yellow. Okay, so if I wanted to make it go back orange, I would have to add acid, which is what I've added now, and it goes back to orange. So you can just change the colour depending on whether it's acid or it's alkali. Okay, and there's your practical example. Let's bring that all back up. Okay, and there you go. Okay, so you do one of two things. It can be interconverted by adding alkali, okay, which removes the H+, okay, which means the equilibrium shifts to the left, or you can add H+, which it'll want to get rid of the H+, and then the equilibrium will move to the right. And that's one of your practical examples, and quite, if I do say so myself, quite a beautiful one in terms of colour. Anyway, that's your little add-on to the video from before, and I hope it makes things easier when it comes time for your exam.